we will try to understand manifold constrained hyperconnections. So we will be going from this residual nets, and then we will go to hyperconnections. This is like 2015 paper that we have. This is from Microsoft, which is residual networks. This is the basic concept behind this. And then we have the hyperconnections, which is by ByteDance, and it came in 2025 March. And then we have the manifold constraint hyperconnections. So these three things are there, so we will understand it and see like what is there in the three of them and understand. So starting from residual networks, what is residual networks is basically we have a block. Okay, let me just draw it like this, and let's say we are going to the next layer. So this is a layer or a block, and we are going to the next layer. So the next layer going to the next layer, and this is the output of the next layer. So from here the learnable parameters, and from here the learnable parameters, they are not coming directly to this. So we are actually making a connection and adding this. So this is basically the whole concept of residual networks, where we are getting the residual from the previous layer. So yeah, mathematically it can be written as this. Model tries to learn complete function h of x, and h of x is f of x plus x. X is the previous layers. This x is added back unchanged through the skip identity. So this is the residual networks that you understand. So yeah, this is the function where we are having this neural network, whatever neural network is there. So whatever is there, this whole neural network thing we have. Okay, I think yeah, so the whole neural network thing we have, and we are getting like, let's see, we will be having this here, we will be having a 1x, and whatever comes here we will be having 1x, and the output will be like this. So this is the whole point of the residual networks. So what is the problem in this? So the problem in this is basically that we have only this x. So in LLMs we don't use this x exactly, we use gated residual networks. Gated residual networks is alpha into x, where alpha is like a scalar where we can like say what is the residual that will go around. So this is one thing. Now why is this important? This resolves the problem of vanishing gradient. It is used in few convolutional layers and self-attention of feed-forward networks in transformers. We will come to hyperconnections now. So hyperconnections, as I mentioned, is a 2025 paper, and what this introduces is it expands the single residual pathway into multiple parallel channels. So what you can understand it like, let's say this is x. Okay, so x will not exactly be a one variable, it will be a vector, because the input will be a vector, right? So x is a input. Now what we do, we use some technique to make this vector into a matrix. Now we will make a matrix out of it. Now what will this matrix do? This matrix will actually keep track of different things and will be used in different ways, and also we will be learning them. It is not like predefined, so we'll be learning the parameters, so when to use, how to use. So yeah, this is widening from 1 to n lanes, n string of residual data instead of 1. We have learnable matrices that control how these strings mix and redistribute information across layers. Okay, so this is the formula that we have. Here you will see that we have HRS, H post, and H pre. This is layer plus 1, this is the layer, and this is just a transpose of this. So what we're doing exactly, first I think I have okay, I don't think I have that here, but yeah, I'll explain it this only. So what we're doing, we are taking a function from, this is basically the layer, and we have this is the vector. So we are taking this vector and projecting this vector into a this is a matrix. Actually this is a matrix. We are taking this matrix and projecting this matrix onto a vector. So first we have a matrix. Where did this matrix come from? I will tell you. First let's understand, we are getting this and getting a we are having this and we are getting a vector out of it. Okay, so this is like HL pre will be used here, and after that we are applying the normalization, the sorry, not normalization, this layer operations, like yeah. And then what we are doing, we are, this layer operation will also give this a vector only. Now we are making a matrix out of this vector, and HRS is another matrix, and we are adding this HRS matrix. So we will be getting XL1 a plus 1 as a matrix. So this is XL and this is XL plus 1. So now you understand that why we are having a matrix here. So yeah, this the output of this hyperconnections will be a matrix and not a single layer output. What does this do? This increases connectivity. Resnet has problems. So representation collapse and vanishing gradient. So these are the problems which we like solve using this. We use this learnable mixing matrices. Yeah, but the problem is, as we increase the number of number of parameters, what happens, like this can amplify signals too much because we have no constraint over these matrices. These matrices have no constraint, so this can amplify or even shrink, like number can grow very big or can become very small, and sometimes it can also like make no sense, and the learnable parameters are making no sense. So what's the obvious answer? So obvious answer is to constrain them. So that's where we have this MHC, manifold constrained hyperconnections. So yeah, you can go through the notes if you want. These are basically very intuitive, and I've also worked out some examples. Now yeah, we will understand what is the H pre, H post and HRS matrices. So H pre has this formula where alpha is a scalar which is also learnable, and other than that we have this gamma, gamma res, this gamma pre, gamma post and gamma res are the learnable parameters, and this is the bias. So this, this and this, these three are the learnable parameters. This and this are the learnable parameters here, and XL is the matrix that we get. So this is the quite the formula for H pre, H post and HRS. That's how we calculate these things, right? So yeah, these are the learnable parameters, alpha scalars, and this. B are the bias vectors, and matrix reshapes the vector into matrix for HRS. Okay, we understand this. This is the formula that we use, and we have worked out an example. Alpha pre and this gamma pre and alpha and beta we have kept, and then yeah, beta will be a matrix of course, because these calculate, this is a matrix of course, so we will be requiring a beta as a matrix. So yeah, we just do the calculation. You can refer to these notes, I will share with you. Then we have H post, and similarly we have HRS. Okay, so this is for this. Now why unconstrained has a problem? It can amplify, it can attenuate or shrink, and it can also make no sense. So this is the problem. Now I have mentioned forward pass. Yeah, this is a better understandable for the formula. We have XL, H pre, it takes it to choose what to feed, and then we have this XL is a this matrix, then H pre converts it into this, then it will be going to the function. Now function will return this, and now this will be going to this, where we will be have a matrix, and then adding this we get this. So yeah, H pre and H post are basically learnable parameters only, but they are more or less like what to like take from this matrix, that is x plus HRS, and no, f of x plus HRS, and what to keep in this vector, right? So that is what HRS is, and H pre is how to make sense of this vector that we get after f, and how to project it into HRS. So that is the main point of these. Now I have done a forward pass, you can go through this. These are very intuitive and very easy examples. Now yeah, we have manifold constrained hyperconnections. So manifold constraint hyperconnections is like we are going to project this residual connection. So yeah, we saw the problem of vanishing and like spiking up too much. So that's why we keep it in this doubly stochastic matrices. So doubly stochastic matrices we keep. What is what is a doubly stochastic matrices? All entries are like greater than 0. Every row sums to 1 and every column sums to 1, greater than equal to 0 actually, yeah. And every row sums to 1 and every column sums to 1. So example is this here, every row and every column sums to 1, right? So this is one double stochastic matrix. So we will make this HRS as W stochastic matrix. We will make all the HCs as W stochastic matrix. So let me just confirm if it is just for HRS or for all. No, I think it is just for HRS that we are doing this. Yeah, we will be doing it just for HRS. So we will take this HRS and do this, okay? And also for H this H pre and H post, we divide by some factor, that is alpha. I think I have not written it here. I have a presentation, I'll show you in a minute. So yeah, that there we will understand that point. So here let's understand this, and we will be taking this HRS and we will be making it to this, okay? So this is the learnable parameters, this is the bias, and this is also the scalar learnable parameter, and we will use the skin hop to make this as doubly stochastic matrix. So for how do we do? So this is a 1965 like written algorithm that we are using here. So quite research went into this, and we exponentiate. So exponentiation makes everything greater than equal to 0, and then what we do, we normalize row and column wise for n iterations, and as n tends to infinity, it will become a doubly stochastic matrix, okay? So yeah, as we know, like in AI, we in engineering in general, we tend to non simplify things. So yeah, we keep n such as it will like 20 or 50 we keep. I'm not sure like what will be the value, but yeah, we keep a large enough n that it will go to a doubly stochastic matrix. Yeah, I think yeah, this is all to for this. Now let me just show you the present. Yeah, so this is what I wanted to show you here. You can see that okay, I think yeah, here you can see this is the HL pre, and what we are doing, we are getting a sigmoid of this, and this is 2 into sigmoid of this for HL post, and skin hop for this. So basically yeah, this is the only thing we are doing here. What will sigmoid do? Sigmoid will make sure that we have non-negative for H pre and H post. So yeah, I'll provide you this along with notes, and I have also written a Medium blog on this, so you can refer to that as well for better understanding. But I hope I made it clear to you. Thank you for watching.